In this video, we will study about spectral distribution of blackbody radiation. With increase in temperature, the energy radiated per unit area per unit time for any surface increases rapidly, and simultaneously the color changes from dull red through cherry red and orange up to a bright white heat. So increase in temperature implies increase in the energy radiated per unit area per unit time from any surface. Further, it is observed that at the same temperature, the rate of energy emission is much less for a bright metal like platinum than for a dull black surface such as an incandescent carbon filament. On the basis of experimental studies, in 1879, Stephens gave a law for the radiation that is known as Stephens fourth power law or Stefan-Boltzmann fourth power law. According to this law, the total amount of energy radiated by a perfectly black body per unit area per unit time is directly proportional to the fourth power of its absolute temperature. तो कोई भी अगर एक परफेक्टली ब्लैक बॉडी ले लें तो उससे रेडिएशन जो होगा पर यूनिट एरिया पर यूनिट टाइम अगर रेडिएशन उसका देखें तो वो रेडिएशन किसके प्रोपोर्शनल होगा, उस ब्लैक बॉडी का जो टेम्परेचर है एब्सोल्यूट टेम्परेचर उसके फोर्थ पावर के प्रोपोर्शनल होगा. दिस मीन्स दैट E is directly proportional to T to the power 4, where E is total amount of energy radiated per unit area per unit time by a perfectly black body, and T is the absolute temperature of that black body. Or we can see that E is equal to sigma into T to the power 4, where sigma is called Stefan's constant. This is a universal constant. Loomer and Pringsheim in 1899 studied experimentally the distribution of energy amongst different wavelengths of the black body spectrum, and the arrangement of their experiment is shown in this figure. The black body radiation were obtained by heating a carbon tube electrically. After passing through the slit S1, these were made parallel with the help of a concave reflective mirror M1. So this is radiation obtained by electrically heated carbon tube, and after passing through this slit S1, कहाँ पड़ रहा है ऑन द कॉन्केव मिरर M1, और यहाँ से अभी ये रिफ्लेक्ट हो जाएंगे और ये पैरेलल रेज ये पड़ रही हैं प्रिज्म पे. दिस इज फ्लोस्पार प्रिज्म. रिफ्रैक्शन होगा और जो ये पैरेलल रेज मिल रही हैं दैट इज फॉल्स ऑन अनदर कॉन्केव मिरर M2. यहाँ से फिर से रिफ्लेक्शन होगा, फिर ये फोकस हो जाएंगी on the slit of a bolometer. This is slit of a bolometer. Actually, bolometer is a device that is used for measuring the heat radiations. By gradually rotating the prism, the radiations corresponding to different wavelengths were focused onto the bolometer one by one, and the intensity is measured. By keeping the carbon tube at different temperatures, a number of observations were made between 621 Kelvin to 1646 Kelvin. The curves were then plotted between the monochromatic emittance E lambda along the ordinate and the wavelength along the abscissa for each of the temperature. In this figure, we can see E lambda versus lambda graphs. इसमें y एक्सिस पे ई लेमडा है. ई लेमडा मीन्स मोनोक्रोमेटिक एमिटेंस और इमिसिव पावर, और एक्स एक्सिस पे वेवलेंथ है. तो इसमें हम देख सकते हैं कि जैसे जैसे टेम्परेचर इंक्रीज़ कर रहा है तो इसमें जो मैक्सिमा है वो भी क्या कर जा रहा है, इंक्रीज़ कर जा रहा है. फॉर ईच टेम्परेचर देयर इज़ अ वेवलेंथ lambda m at which the energy radiated is maximum. This is lambda maximum for the curve at temperature T3. Lambda maximum 3. इसके लिए देखिए ये ई लेमडा जो है यहाँ पे मैक्सिमम है. दिस इज ई लेमडा 3. ई लेमडा ये मैक्सिमम है. उसी तरीके से टेम्परेचर अगर T5 लें तो ये रहा, दिस इज लेमडा फॉर टेम्परेचर T5, lambda maximum, and this is E lambda maximum for curve at temperature T5. With increase in temperature, the maximum shift higher but towards lower wavelengths. तो जैसे जैसे टेम्परेचर जो है वो इंक्रीज़ कर रहा है, वी कैन सी फ्रॉम दीज कर्व्स दैट ई लेमडा इंक्रीजेस. ई लेमडा तो इंक्रीज़ कर रहा है, बट जो करस्पॉन्डिंग लेमडा मैक्सिमम है लेमडा एम, दैट इज डिक्रीजेस. हाई द टेम्परेचर, मोर प्रोनाउंस्ड इज द मैक्सिमम. The area under the curve of a particular temperature gives the total energy emitted by the black body per unit area per second for the complete spectrum that is corresponding to all the wavelengths at that particular temperature. Similarly, the area under the curve increases with increase of temperature, and it is found that the area is proportional to the fourth power of the absolute temperature. As the area under the curve represents the total energy emitted by the black body per unit area per second, hence EB is proportional to T to the power 4. This is Stefan-Boltzmann Boltzmann law. From the curves, it is also found that lambda m1 into t1 is equal to lambda m2 into t2 is equal to lambda m3 into t3 and so on. That is lambda m into t is equal to constant. This implies that lambda m is proportional to 1 by t. Thus the wavelength lambda m for which the emittance of a black body is maximum is inversely proportional to its absolute temperature. This is known as Wien's displacement law. So according to Wien's displacement law, the wavelength lambda m for which the emittance of a black body is maximum is inversely proportional to its absolute temperature. That is, lambda m is proportional to 1 by t, where t is absolute temperature of the black body.